Alrighty, in this video here, we're going to talk about 4.1, which is sample spaces and probability. So probability is the chance that an event occurs. Probability is the basis of inferential statistics. So again, if there is, let's say you have 4 marbles, each marble would have a 1/4 opportunity of being selected. So that's pretty much kind of how that is. So then we have objective 1 here, which is determine sample spaces and find the probability of an event using classical probability or empirical probability. So our basic concepts here. So processes such as flipping a coin, rolling a die are called probability experiments. So you do the probability. Empirical is things like what should happen. So again, if you're flipping a coin or rolling a die, this would be probability experiments. So let's look into that. So a probability experiment are chance with basically a chance process that leads to well-defined results called outcomes. So again, if you roll a dice um, and write out the results when you get a 1, 1, 6, 4, 2 or something like that, right? So then the probability experiment would be that you got a 1, 2 out of 5 times. So 40% of the time you were getting a 1. So again, outcomes are a result of a single trial of a probability experiment. So in a probability experiment, you are doing the actual probabilities, or I say the probability, doing the actual like experiment, but then each result is represented as an outcome. So like I said, you might roll the die 5 times, you might get 1, 1, 2, 6, 3, or something like that. So therefore, each one of these would represent the outcome. The entire thing, each one was called a probability experiment. And then when you do the probability experiment, then you know you have 2 out of 5 of rolling a 1. So you have a 40% chance of rolling a 1 with that data. A trial again means flipping a coin once, die once, answering a multiple choice question with 4 selection. So when tossing a coin, there are only 2 outcomes. You have either heads or tails. A multiple choice question has 4 options, A, B, C, or D. Sample space is basically the set of all possible outcomes of a probability experiment. So your sample space is all the outcomes. Like for tossing a coin, you have heads or tails. There's your sample space. Those are the options that you'll get. Rolling a dice, you have 1, 2, 6 options. Again, 6 options of in the sample space. You might not get all 6 of them, but there's only 6 things. Answering a true or false, you have 2 options. Tossing 2 coins, now you have 4 options because you head, tail. Right. So again, sample space are just all the possible outcomes in an experiment. These sample spaces have been found by observation and reasoning. Charts and tree diagrams help organize these possible outcomes as well. So in example 1 here, it says sample space for rolling 2 die. So we're going to find the sample space for rolling 2 die for 2 die. So each die can land 6 different ways, and 2 dice when 2 dice roll. The sample spaces can be shown in an array. So this is called an array. Basically, have like little parentheses with each option. So the issue is a lot of people don't understand. But if I roll a 1, then I can roll a 2. And then you might also realize I can roll a 1 on this die and a 2 on this number. So even though you roll the die, 1 and 2 and 2 won't have the same total numbers, but they are two different outcomes. Think of it like as if you had like a red die and a green die. So like a red die and a green die. So you would say outcomes that you could get would be a 1 on a red die and a 1 on a green die, and then a 1 on a red die and a 2 on a green die, which would be a totally different outcome when I get 2 on a red die and 1 on a green die. So then, again, two separate things. So you can also see here by doing this as well, if I have 6 different outcomes for one die, 6 different outcomes for another die, I just do 6 times 6, I'll find out I have 36 different options in my sample. Okay. And you kind of see that in that next sentence. There are 36 different elements in the sample space. Using the chart, we could be sure we listed each pair without repeating any or leaving any out. So it's nice of them to give this to you. I know writing it out for the first time could be things that you might not have assumed. Another method to find all possible outcomes of a probability experiment is to use a tree diagram. So in example 2, we find the sample space for the gender of 3 different children in a family. So in a family of 3 children, find the sample space for the order by gender of the children. So again, each time a child is born, there are only 2 possibilities. You can either be a boy or you can be a girl. So you would draw 2 branches from the firstborn child, do the same for the secondborn child for each of the firstborn options, and repeat. So what that means is, so in this right here, here you go. You're pregnant, so you can either have a girl as the first child. After you have the first child, then it splits off. So then if you have a boy, you could have another boy, or you could have a girl. If I have a girl first, I can have a boy or have another girl. After I get to the second child, same process. Once I have the second boy, I could end up with a third boy. Or I could finally get a girl and have boy, boy, girl. Or maybe I want boy, or maybe I want boy, girl, girl, and then I have this combo. Or maybe I went girl, boy, and then I have this one, girl, boy, girl, and had this option. Or and I went girl, girl, finally had that boy, and there we go right there. So or I could go for girl, 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 have this option. So you can see for the sample space, there's 1, 2, 3, 4, 5, 6, 7, 8 different options that you could have for someone having 3 children, right? So again, a tree diagram can help illustrate that as well. So the results for each possibility is a combination of 3 different outcomes, because again, they're having 3 kids. Consists of a set of outcomes of a probability experiment. So these are all events. My first event being that I had girl, 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 right? So that's my outcome. It's also can be considered an event as well. So an event can be an outcome or more than one outcome. So your event could be what's the probability of getting 2 girls out of 3. So that could be a set of like girl, girl, boy, girl, boy, girl, boy, girl, girl. So now I have multiple outcomes within my event. So an event with exactly one outcome is called a simple event. An event with more than one outcome is called a compound event. So if I want to know what's the probability of getting all girls, there's only one outcome, simple event. But if I ask what's the probability of getting 2 girls, now I had multiple outcomes. So now I have a compound event. So three interpretations of probability. You have classical probability, which uses samples spaces to determine the numerical probability that an event will happen. Classical probability assumes that all outcomes in the sample space are equally likely to happen. For instance, assuming marble of same size, same shape, same feel, things like that. So they're all equally likely to get chosen. I do apologize for those seconds that it seems like nothing's happening. My headset keeps going in and out, so that only lasts like less than 5 seconds. So if a sample space has n equally likely outcomes and an event A has k outcomes, then the classical probability is as follows. So basically, to find the probability of an event A happening, you would take the number of outcomes for actually happening. So for instance, if I wanted the probability of two girls, I saw that there were three options. I could either do girl, girl, boy, boy, girl, or boy, girl, girl, but there was a total of 8 outcomes. So then this would be the probability of getting two girls, right? This is how a classical probability be written. And then you can turn it decimal, multiply by 100, now you have a percentage, whatever the outcome of the question is asking for. So let's look at example 3. We want to find the probability referred to in example 2. What is the probability that all three children are of the same gender? So again, it breaks it down. You have 8 outcomes. These are your 8 outcomes written by the tree diagram. And then there's only 2 outcomes that have the same gender. They're either all boys or they're all girls. So for example, the A, this is your A, the event that's happening, three children that have the same gender would be two, but they were still 8 total in the sample space. You reduce that, and now you get a 1 in 4 chance of having all three being the same gender. So 25% chance in a sense. All right, so probability rules. There are 4 characteristics of probabilities. We use them to solve probability problems, so, understanding the nature of probability and deciding whether answers to probability problems are correct, meaning are they realistic, right? So the probability of event, of an event is between 0 and 1. You can either not have an ability to get that event. So let's say I wanted to know what is the probability of having 4 girls? Well, since there's only 3 kids, that would be 0. Or again, maybe I wanted what the probability of having a combination of boys and girls, but have 3 of them. Well, that would be all of them, so that would be 100. So you can have a probability again between 0 and 1, also written as the probability of the event happening has to be between 0 and 1. If you take those fractions, turn them into decimals, you can see that they would give you decimals that are less than or greater than 0. Equal and can equal 1. So do keep that. So again, 0 just being impossible. You have unlikely if you're between 0 and 5. You're likely if you're between 5 and 1. 50 shot right. It's So in example 4 here says probability of rolling one die. So let's consider one standard fair to apologize for the technical difficulties. So again, we have a fair die, no loaded die. Part A wants to know what's the probability of rolling a 5. And then part B wants to find the probability of rolling a multiple of 3. So when we look at this, you need to realize a die has 6 options in their sample space. That's either 1, 2, 3, 4, 5, or 6, each of which is equally likely to be landed on. If I'm rolling 5 on the first try, exactly 5, that would mean there's one of the 6 options. So there's one sample space that gives me a 5, but there were 6 total. So in this case, this would be a 1 out of 6 chance. Rolling a multiple of 3, well, you got to realize what numbers can be divisible by 3. You have 3 and 6. So I actually have 2 of these sample space outcomes that would be a multiple of 3. I would still have 6 options. Then we can reduce that to have a 1 and third chance of actually getting a multiple of 3. All right. This last one here, 2, the sum of the probabilities of all outcomes in a sample space must equal 1. A 5 or 6, you would find all the probabilities to be 1/6, and they all add up to 1. It is an incorrect probability. We'll see some of those too later. All right, so on part 3 here, it says if an event A cannot occur, that is, the sample space is empty, there were none to give you that option, or the event is impossible, the probability is 0, meaning the probability of the event happening is 0 when an event A cannot occur. So for instance, maybe I wanted to know what's the probability of rolling a die and getting 0. 0 is not in the sample space, so not possible. So then I get 0 out of 6, which is 0. So that's an impossible event. Look at example 5 for another impossible event. We want to find the probability of rolling an 8 when rolling a standard fair die. Remember, a standard fair die is 1, 2, 3, 4, 5, and 6. 8 is not an option. So there is 0 options or samples in the sample space that has an 8. Because again, it is impossible on a 6-sided die. So on part 4 here, if an event A is certain, the probability of A is 1. So the probability of the event happening is 1. So if you wanted the probability of like getting either 1, 2, 3, 4, 5, or 6, well, those 6 options, that would be 6 out of 6, which would be 1. So it's certain that you would definitely get 1 out of 6. So let's find a certain probability. So we want to find the probability of a certain event and find the probability of rolling a value less than 7 using a standard die. Well, since all 6 of my options are less than 7, rolling a die less than 7 would be a guaranteed probability. So it's a certain probability that has to happen. Because all outcomes when rolling a standard 6-sided die, a fair die, are less than 7. All right, let's talk about complementary events now. So a complementary event is the complement of an event A is the set of outcomes in the sample space that are not included in the outcomes of event A. We typically denote it as a bar. So if I wanted to know the complement of rolling a die of 5, that would mean I want all the other options that are not a 5. Out of 6. So the complement of that would be all the other outcomes, which would end up being 5 out of 6, because that would be 1, 2, 3, 4, 6. So in example 7, we're going to find the complements of these events. So event A here, we're going to select a day of the week that begins with T. That is Tuesday and Thursday. So that would be 2 out of 7. Event B, roll 2 die and get a sum that is an odd number. That is the sum of 3, 5, 7, 9, 11. So that's 1, 2, 3, 4, 5. And just so you know, there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different outcomes you can get added up. So I have a 5 out of 11 probability of rolling sum that is odd. Okay. Let's check this solution here. So if I wanted to know the complement of A, so I want to now know what is the complement of A. Well, since I know the probability of A was 2 out of 7, then the complement will be all the days that aren't Tuesday and Thursday. So that would be, I guess, they have space here. So we would select Monday, Wednesday, Friday, Saturday, and Sunday, giving me a 5 out of 7 as the complement. All right. Part B, again, the complement of a roll and a die that is not a sum is odd. So that would mean that that would be 2, 4, 6, 8, 10, 12. So I would have 1, 2, 3, 4, 5, 6 out of 11. That's my probability. So if the probability of an event or the probability of its complement is known, then the probability of the other can be found by subtracting the known probability from 1, which is kind of what I was doing, but the and the complement have to add up to 1. So if I know the complement, I can do 1 minus, to get the complement, I can do 1 minus the event happening. Or if I want to know what the event happening, I could do 1 minus its complement. Or to check it, I can take the event plus the complement and it better equal 1. So sometimes it actually is a little bit easier to figure out the complement, take it away from 1, get the event. Rather than trying to find it, because the event might be so large in sample that you'd be there forever trying to calculate it, but like the complement of it not happening might just be like 2 or 3. You go, well, I can just subtract it from 1. Now I have my total answer. So sometimes this does become an easier method. We'll see some throughout this chapter. All right, so let's talk about empirical probability. So empirical probability relies on actual experiments or observations to determine the likelihood. So you have classical probability, what should happen. Then you have empirical probability, what actually happened. Did you actually roll the die 6 times and got one of each number, or did you end up getting 2 or 3 or 4 of the same ones? It kind of goes through that relative frequency. How many times did you get each one? So given a frequency distribution, the empirical probability of it happening The frequency of the event happening divided by the total amount of experiments that went on. So let's look at example 8. A survey of blood types of 50 people revealed that 21 had O blood, 22 had A blood, 5 had B blood, and 2 had AB blood. So frequency table, one of 5 probabilities. Want to have the probability that so O, O blood. I can just go, all right, there were is that right? Let's look at the chart. 21 had O blood, so this is actually, so if I wanted a person that had O blood, that would be 21 out of 50. So a person has type O blood. So it's 21. That was the frequency divided by the total, which is 50. If you don't know, so you can leave it like that. So a person had A blood or AB blood. Well, A blood is 22 out of 50. AB blood is 2 out of 50. So if I just add that up, so anytime you see the word or, you want to add. I add those up, that gives me 24 out of 50, reduced down to 20 out of 25. If I want a person to have neither, I know what the probability of A and AB is. If I'm looking for NOR, I'm really looking for the complement of this. So I can do 1 minus 12 out of 50, and I would actually get 18 or 12 out of 21 minus 12 out of 25, which is 18. Nope, I lied. That's only 30. Hold on. That would be 13 out of 25. All right, so empirical probabilities have the same value as the relative frequencies of the and the distribution. So that's all this. This is all incorrect, so make sure you fix that on your notes. All right, let's talk about law of large numbers. Law of large numbers is the law of large numbers. So the law of large numbers states that as the number of trials of a random experiment increases, the empirical probability will approach either the classical or the theoretical probability. So remember, classical and theoretical is the things that should happen, right? So the empirical probability is just stating if I flip a coin twice, I can end up getting 2 heads. But if I flip a coin 200 times, I should be a lot closer to 100 heads and 100 tails. So the larger my experiment is, more experiments I have, larger the the closer my empirical probability, my classical or theoretical. So what actually happened versus what. Alrighty. I think it's working. All right, so in this one, suppose a fair die is tossed. The classical probability for each value from 1 to 6 is 1 out of 6. For an experiment using a fair die, as the number of tosses that result in a 2 increases, the empirical probability of tossing 2 will approach the theoretical probability of 1 out of 6. So I might throw the die out 20 times, but I might end up getting 1/5 or something like that. But if I do it 200 times, I get a lot closer to that 1/6. All right. So if a die is tossed many times and the empirical probability tossing a 2 is not approaching 1/6, then it's likely that the die is probably not fair. Maybe you're dealing with a loaded die. So if you roll 200 times, the outcome of each one of those numbers is not getting to 1/6, then the likelihood is it's not a fair die. There's cheating going on. All right, so we do have probability. This will be the last thing we talk about in this video. So subjective probability is based on or estimate in actual information. The probability tends to be based on the experience, the evaluation of a solution. For instance, the forecast is a 60 or a sports writer might say there's a 70% chance that a particular team will win the pennant that year, are examples of the use of subjective probability. They use their experiments, their calculations and stuff, but this would just be a prediction. We think there's a 65 in the area, there's 65% of y'all that are going to get rain. You have a chance of getting rain. And then the 70% chance basically is just stating that, hey, with looking at my data, I feel that this team has a 70% chance of winning. So that would just be a subjective probability. All right, so I'll conclude the video there, and then I'll break down the next 4 topics. See you in the next video.